Alright guys, today we're going to begin our discussion on ethers and epoxides. So, let's first talk about ethers. What is an ether? Well, the general formula for an ether is this, ROR, in which the R group can represent any alkyl. Now, ethers come in two categories. They can either be symmetrical, in which the R groups attached to the oxygen are the same. So, for example, if I were to have two ethyl groups attached to the oxygen, the ethyl groups obviously are the same, so this would be classified as symmetrical. The other category is what we call unsymmetrical. And as you can pretty much imagine, an unsymmetrical ether is one in which the alkyl groups are going to be different. So, if I were to replace one of these ethyl groups with, say, a methyl, this would be classified as an unsymmetrical ether. In terms of nomenclature, ethers are pretty simple. There are a couple of ways in which you can name an ether. I'm just going to share the one that I use, which I believe is probably the easiest way. So, in terms of nomenclature, it is really about naming each alkyl alphabetically. Plus the word ether. So, in the case of my examples that I just drew, okay, since I have a methyl group here, and an ethyl group here, so methyl, ethyl, alphabetically E comes before M, so this would be referred to as ethyl methyl, two words, not one, ether. Ethyl methyl ether. Now, what if the alkyl groups are symmetrical? Well, we just saw one of those. what if I had, I believe my other ether was one of the two ethyl groups. So if I have two like alkyl groups, meaning they're both, in this case, ethyl. Well, we got two options. We can either call this ethyl ether, or if we take into consideration that there are two ethyl groups, obviously, we could use the Greek prefix for two and call this diethyl ether. Pretty easy, yes? Okay, so I guess the next thing that we need to discuss is, how do you make an ether? Well, we've already talked a little bit about making ethers, particularly the symmetrical kind. So I'm going to start with the symmetrical ethers. And we actually saw those in the last chapter. Remember, we said that if you had a primary alcohol any primary alcohol and we heat that alcohol in the presence of a strong acid such as sulfuric at about 140 degrees C, we'll get an ether. Now, when we discussed this, I don't remember if I said that this process only works for symmetrical ethers. I probably didn't, because at that time we really weren't focusing on ethers as much as the alcohol. So I'll say it right now. This process only works with symmetrical ethers, meaning I gotta have two of them. Okay? So if I have two identical primary alcohols, I heat them at about 140 degrees C in the presence of sulfuric acid, I will get a symmetrical ether. Now, I guess that kind of opens up a new question for us. What if the alcohols are not the same? I.e., we're talking about making unsymmetrical ethers. Obviously, I think it stands to reason that we have more options than to make symmetrical ethers. And the method that we're about to talk about right now was really described by a chemist named Williamson. So we're going to talk about what is now referred to as Williamson synthesis. And in parentheses, I'll say of unsymmetrical ethers. Okay. Well, what Williamson found was that if you combined an alkoxide with an alkyl halide, you could get an ether. So again, I guess the obvious question is, how? So let's talk a little bit about the mechanism. So first I got to start with an alkoxide. Do we all remember how to make an alkoxide? Well, alkoxides are derived from alcohols, but you probably already knew that. If you have an alcohol, and it really doesn't matter what kind of alcohol, so I'll even say in parentheses, any alcohol. Doesn't matter whether the alcohol is primary, secondary, tertiary. If I react that alcohol with a strong base, strong base, and nothing exotic, could be something like saturated NaOH or saturated KOH, doesn't matter. That base will extract the hydroxyl proton from the alcohol I'll have a little bit of water as a byproduct, but looky there. That's my alkoxide. Okay. Okay, so once we make our alkoxide, and remember, we said it doesn't matter what kind of alcohol is the parent to the alkoxide. The alcohol itself can be primary, secondary, tertiary, it does not matter. Okay, so Once we got the alkoxide, we said we need an alkyl halide. So here's my alkoxide again. Okay. It's down a little bit so you can see. If I have say, how about an ethyl? Halide. It's as good as anything, yes. Remember that the carbon attached to the halide creates a small dipole moment. And this carbon is electrophilic, meaning it's partially positive. Well, the alkoxide is about as nucleophilic as you can get. So I've got an electrophile, and I got a nucleophile. Yes? Well, what do you think is going to happen? Well, if you said, hey, I bet this alkoxide is going to come in, hit this electrophilic carbon, and force out the halide, man, you are right on target. And that's exactly what happens. So, the halide is gone, and essentially, I've got my ether. Does anybody remember what type of mechanism this represents? Yeah, that's right. I think I heard it. Someone said that this was an SN2 mechanism. For those of you who didn't say SN2, I'm going to assume that's what you were thinking. You had it on the tip of your tongue and you were getting ready to say, hey, I think that's an SN2 mechanism. And you would, again, be absolutely correct. Would you like to see an example of this in action? Why not? Why not? Get some more paper. So, let's say I'm going to start with T-butanol. Remember, we said it doesn't matter what kind of alcohol. Not in the least. Okay? So, we said that alcohol in the presence of a really strong base will take off that hydroxyl proton from the alcohol will make water, and we will get an alkoxide. Now, since the alkoxide is derived from T-butanol, we're going to call this T-butoxide. Okay? All right, so I got my alkoxide. Give myself a little bit more room to write. Now, I need an alkyl halide. So there's my alkoxide. How about we use, I don't know, methyl chloride? That sounds good. Does it matter what type of halide you're using? Not really. Most of these reactions tend to prefer chlorine or bromine anyway. I would just stick with that since it seems to work for our purposes. So we said this was an SN2 type mechanism. So the T-butoxide will hit the methyl carbon, thereby forcing out the chlorine. So there's the chloride gone. All right. And we are going to be left with an ether comprised of a methyl group and a T-butyl group. Now, how would I name this? Now, let me stop you before you make a mistake, and this is a common mistake. The T in T-butyl refers to tertiary, right? Tertiary is just an adjective for the type of butyl. Remember, there are many different types of butyl groups. There's T-butyl, sec-butyl, isobutyl, N-butyl. Even though it's tert-butyl, and you would think methyl would come first, we go by the butyl. So B comes before M. So this would be referred to as T-butyl methyl ether. Okay? Now, this is all well and good, okay? But, you know, I just thought of a question that we haven't asked. The whole time that we've been doing this Williamson synthesis, we said that the type of alcohol from which the alkoxide comes from doesn't matter. That you could make an alkoxide from a primary, secondary, or tertiary alcohol. You know what we didn't ask? Does the nature of the alkyl halide matter? Huh, that's a good question, isn't it? Yeah, I know it's a good question. That's why I asked it. So let me say that again. Here's our new question. In Williamson synthesis, does the nature of the alkyl halide matter? You know there's a catch. You just have to know there's a catch. And the answer is yes, absolutely. The alkyl halide must be primary. Why? Well, you got to think back to the discussion that we had way back when on nucleophilic substitution. Okay? What if oh, this is a good one. You're going to love this one. What if instead of reacting T-butoxide with methyl chloride, what if we reacted with T-butyl chloride? Now, I've got two T-butyl groups. Kind of tempting to say that you're going to get a symmetrical ether, isn't it? And I already know on the exam, somebody is probably going to do this. They want to write me a beautiful ether with two T-butyl groups. Right? Wrong. This is wrong. Okay? Let me show you what will happen in real life. So, okay. So, we would say that in reality, this is what's going to happen. The T-butyl group or rather the T-butoxide, sorry. T-butoxide will come along. Now, in Williamson synthesis, the alkoxide acts as a nucleophile. And we saw that the alkoxide came and it attacked the methyl chloride to force out the chlorine. But you have to remember that nucleophiles also can be fairly strong bases. Now, because the chlorine was attached to a tertiary carbon, the chlorine is lost almost spontaneously. In fact, let me just draw it up here for you so you can see. But T-butyl halides are very easily dehalogenated. In fact, you can take T-butyl chloride and just shake it up real good, and you can lose the chlorine. Okay? And this is near spontaneous. But what's really important is look what you have. You have a tertiary carbocation, don't you? Well, what if your alkoxide, instead of acting as a nucleophile, acts as a base and extracts a proton? Remember, you've got two very, very sterically hindered compounds. In this case, elimination is going to be favored over substitution. So you'll get a little bit of T-butoxide forming, but the main product is not going to be an ether. It's going to be an alkene. Okay? So, the take-home message with regard to Williamson synthesis is that successful Williamson synthesis requires an alkoxide plus a primary alkyl halide. Okay? If instead the alkoxide reacts with either a secondary or tertiary alkyl halide, you'll get an alkene. So this is a perfect example of how nucleophilic substitution can compete with elimination. Okay, so now that we've gotten synthesis and nomenclature and all that other good stuff out of the way, we probably need to say something about reactivity of ethers. This isn't going to be too bad. There's really only one reaction that I'm going to hold you responsible for. Ethers don't react with a whole lot of other things. I wouldn't say they are inert just because of how volatile they can be. But the only reaction that we're going to discuss is how ethers react with hydrogen halides. And the result, not exactly what you expected. It's typically going to be two alkyl halides. Now, does it matter whether the ether is symmetrical or unsymmetrical? Not really. So the ether can be either. So it can be symmetrical or unsymmetrical. Okay. So let's talk about how this comes about. For my example, I'm going to use an unsymmetrical ether. So I'm going to use ethyl methyl ether. And I'm going to react it with, let's say HBr. So my claims state that by the time the reaction is complete, I'm going to get two alkyl halides. I'm going to get ethyl bromide and methyl bromide. How? Okay, let's look at the mechanism for this, shall we? Okay. So, here's the ethyl. Here's the methyl. Now, probably come as no great surprise that the oxygen of the ether will be attracted to the proton of the hydrogen halide. And I'll get rid of the bromine. And I'll come away with a protonated ether. Now, at this stage, I no longer have an ether. Okay? I've got something that's somewhere in between. But here's what's going to happen. The bromide, acting as a nucleophile, will come in, hit the carbon, and I'll get, look at this, ethanol and methyl bromide. Now, I already know what you guys are thinking. Why did the bromine attack the methyl carbon? Could it have attacked the ethyl carbon on the left side? Yeah, it could have. Remember, in the end, you're going to wind up with two alkyl halides. So unless there are some kind of steric considerations that we need to take note of, it really doesn't matter where the bromine will hit. Excuse me, the bromide. It doesn't really matter where. Okay? So, is the reaction done? No, not even close. See, once we have an alcohol, the alcohol, in this case, is going to react with a second mole of HBr. And when it does that, the reaction is going to go pretty much as you would expect. So I'll get my second alkyl halide. Now, again, this could have gone the other way around, in which the first mole of HBr hit the ethyl portion of the ether. Again, it really, really does not matter. Okay? So, take home message in this case is that ethers can and do dissociate into two moles of alkyl halides with reaction to a hydrogen halide. Okay, guys, this wraps up the first part of our discussion on ethers and epoxides. I thank you for your cooperation and attention, and I will talk with you soon.